Hello, class. This is Mr. Hart, and in this podcast, I want to talk about how we can store energy. So, if you think about energy, it's the ability to do work, right? To move an object over a certain distance. Okay, but there are lots of things that can store this energy. Okay, think of like a battery or gasoline. Okay, if I put gasoline in my car, it's not going to move my car right away, right? I have to actually ignite it and put it through the engine before it'll move my car. But until then, it's storing that energy, right? So gasoline can actually store energy until we need it. Okay, so there's actually two types of energy that we want to know. Okay, there's potential energy, okay, which is the energy that is stored in some form, and there's kinetic energy, which is energy of motion, basically when we're actually using the energy. Okay, and so there's lots of different ways we can have potential energy or store energy, right? So a couple of them include gravitational, chemical, elastic, electric, thermal. Okay, all these things can store energy until we need it for later. Okay, so for example, if I put a boulder at the top of a cliff and I just let it sit there, it's storing energy that I can use later. Once I push the boulder off the ledge, it's going to start moving. Okay, so gravity can actually store that energy until I need it for later. Okay, chemical energy, again, like gasoline. Once I put it in my engine, or in my gas tank, it stays there until I put it into my engine, and then I can move my car with it. But until then, it's stored. It stays in the chemical form until I need it. Okay. Same with like food. Okay. Um, for our bodies, we need energy to move around, right? We get that from our food. So the chemicals in our food store the energy until we use them and we digest them and things like that, and we can use that energy later. Okay. Elastic energy with springs, for example. Um, you just think about if you press down on a spring, it's obviously going to be able to push back on you once you release the spring. Okay, if you think about a trampoline, for example, when you jump on the trampoline, it's storing energy to push you back up into the air. Okay, electric energy, obviously batteries and things like that. You want to be able to run your electronics or use energy to run your electronics unless the batteries are storing it. Okay, and then there's thermal energy. So heat can actually store energy as well. If you think about steam, steam can move a lot of things. That's what the steam engine was based on. Steam turbines use thermal energy to move as well. Okay, so all these things store the energy until you need it to actually move. Okay, so in class we did a lab called Forms of Energy, which kind of showed some of these different things. Okay, but let's move on to gravitational energy. So gravitational energies, one we'll discuss a lot in this class because it deals with motion. Okay, again, a boulder falling off a cliff or a book that's about to fall off a shelf, those things are storing gravitational energy. Okay, so we can actually calculate how much energy we're going to use. Okay, so the potential energy is equal to the mass of the object times the gravitational acceleration times the height. Okay, so if I take the mass of the object, take gravitational acceleration, and then I times it by the height, or how high it is above the ground, I can calculate how much energy I have. Okay, and so the other cool thing is if energy is a transfer, or work is a transfer of energy, right? Or energy is the ability to do work. Okay, so if I take the mass times the gravitational acceleration times the height, I can actually figure out how much work I can do with that boulder. Okay, so this is actually going to be measured in joules. Okay, energy is measured in joules just like work. Okay, and so we can calculate that out. Okay, so let's try an example problem really quick. So a 150 kilogram boulder is at the top of a 350 meter tall cliff. How much potential energy does that boulder have? Well, we know that the mass of the boulder is 150 kilograms. And we know that the height above the ground is 350 meters. Okay. So now from here it's really simple. We know that the potential energy equals mgh. We know m, we know g because it's a constant, we know h, so it's just going to be equal to 150 times 9.8 times 350. Okay, and so let me pull out my calculator really quick. And when we plug those all in, we get 514,500 joules. Okay, so there you go. So that boulder has quite a bit of energy stored in it, right? If I wanted to move something using that boulder, I could do 514,000 joules worth of work on the object, okay, using that boulder. Okay, so it can transfer quite a bit of energy because it's so high up. And this makes sense. If a boulder fell off a 350 meter tall cliff, you wouldn't want to be underneath it because it has a lot of energy to it. Okay? All right, so hopefully that's simple enough. If you're doing this for participation, try this one on your own. Okay? A man lifts a 20 kilogram box 1.5 meters into the air. How much potential energy does the box have? Okay, so see if you can work that one out. All right, so not only can we calculate the potential energy or how much energy an object can store, or a certain object can store, but we can actually calculate how much energy an object's using. Okay, so we call this kinetic energy, right? Once an object's actually moving, it has energy to it as well. Okay, so we call this kinetic energy. So kinetic energy equals 1/2 mv squared, or the mass times the velocity squared. Okay, so this is mass. And this is velocity. I apologize for the sloppy handwriting on the trackpad. Okay, so if you think about it, would you rather be hit by a baseball that's going 100 miles per hour, or a, let's say, a giant boulder going 100 miles per hour towards you? Okay, obviously, the smaller the object is, the better generally, right? A more massive object is going to have more energy if it's moving the same speed. Likewise, if you had a baseball going 100 miles per hour or a baseball going 20 miles per hour, you're going to want to have the one that goes 20 miles per hour because it's going much slower. It doesn't have as much energy. Okay, so this kind of makes sense, right? If an object's going faster, it has more energy. If it weighs more or has more mass, it also has more energy. Okay, and so when we are storing energy, we have to think about how much energy do we need to go a certain speed and things like that. So this becomes a very useful equation to know. But let's go ahead and try an example. Okay. So a child on a bike has a mass of 40 kilograms. If the bike is moving at 6 meters per second, how much kinetic energy does the child on the bike have? Well, we know that the mass of them combined is 40 kilograms. Okay. And we know that they're moving at a velocity of 6 meters per second. Okay. So we can figure out how much energy this system has, this child and this bike moving together. All we need to use is our equation. So the kinetic energy equals 1/2 mv squared. Okay, we know m, we know v, so we just got to plug it in. So 1/2 times 40 times 6 squared. So I'm just going to warn you right now, a lot of people forget to put the squared there. Make sure you don't forget it, okay, on all the kinetic energy problems. So if we calculate that all out, let me get my calculator out again, we get 1/2 times 40 times 6 squared, which is 36. Okay, so we get 720 joules. Okay, and there you go. Hopefully that's simple enough, but we can figure out how much energy that child on the bike has. Okay, obviously not as much as the boulder had when it was on top of the cliff, because it's going to hurt a lot more if a boulder falls from that height than it is if a kid runs into you with his bike. Okay, All right. But that's all we want to cover for now. So hopefully you know how to calculate the potential and kinetic energy and kind of understand what they are. If you are answering this or watching this video for participation, see if you can answer this one with kinetic energy. Okay, so 1,000 kilogram car has a velocity of 60 miles per hour. How much kinetic energy does the car have? Okay, all right, but again, potential energy, kinetic energy. We'll do more of these in the next week or so, but right now we just want to know how to calculate them so we can use them in other applications. But these will become very important things to know. But hopefully that all makes sense. Let me know if you have any questions, and thank you for watching.